Your second video on severe weather is going to take us through the 3 stages of thunderstorm development. Now you should have received a set of 3 pages that have the 3 different stages shown for thunderstorm development. The first picture should look something like this. Now I've taken this color picture and sort of stripped down the color so it's a little bit easier to copy it off without having to use so much toner, so it doesn't look quite like this, but the general idea is still there, and most of the numbers and the shapes and the arrows and things are still there. So I'll have you fill in, basically you can put all the notes that go with this entire video right on these 3 pages and the 3 stages of thunderstorm development, including some maybe arrows to sort of label and show where some features are in the clouds as they start to grow. One thing I'll mention real quickly is that the heights that you see on the side here, 10,000 up to 40,000 feet, are somewhat approximate numbers. Don't get too hung up on numbers or anything, or that the bottom of this cloud's at 5,000 feet or so, so every cloud that's a thunderstorm starts at 5,000 feet. That's not always the case. And it'll go up as high, you'll see at the second stage, is beyond 40,000 feet. There are places where that absolutely happens. There are plenty of storms that go way beyond that, 60,000 feet, perhaps even more. Depending on the height of the tropopause, that can vary a lot. So a couple notes to have you put down on each of these pages. This video shouldn't be too terribly long, but you want to get these high point ideas next to each picture, and then some labels that'll kind of point out to you as well. So the first stage of a thunderstorm's development begins simply with a regular old cumulus cloud. Now we haven't gone through the real common types of clouds. You should have seen those at some point in an earth science class. And so a cumulus cloud is basically just a little lumpy cloud, fair weather looking cloud sometimes. It's the ones that you see that look like animals or something floating across the sky. And a cumulus cloud, a cumulus comes from a Latin word that basically just means to pile up. This is why you see the same letters in the word accumulate. So accumulate and cumulus both sort of have this root in piling something up. As you accumulate things, they pile up as well. So a cumulus cloud is just a cloud that's piling up. And so as this stacks up vertically, you're starting to see this white condensation or even ice starting to pile up vertically. So a cumulus cloud in the first stages of a thunderstorm will start to grow very, very vertically. And it starts with a flat bottom there where the temperature and the dew point meet, the cloud begins to form, and then it starts to pile up from there. Maybe the cloud gets to 20,000 feet or so up above. And you'll notice here at this stage of the thunderstorm's development, this isn't a thunderstorm yet by any stretch, but you'll see the yellow arrows here at the bottom of the cloud show the air moving entirely up and into the cloud. Nothing flowing downward at this stage. All the air movement at this point is upward with some kind of swirling turbulence along the edges of the cloud. If you get in a helicopter or plane, you're near one of these as they're starting to grow, you can actually see the billowing edges of these as if it's erupting from inside, and it's pretty cool. You can see it on lots of high quality videos that are out there, TV shows that show clouds up close, and it's usually shown in fast forward because the billowing isn't happening like smoke. But when you watch it in fast forward, it's pretty cool, and it actually looks like the cloud is sort of exploding from within, which it kind of is. So the air movement is dominated at this point by upward movement of air, updrafts into the cloud. When we get to the second page, in the second image, you'll start to see updrafts and downdrafts, and then by the end you'll see downdrafts only. So it's just kind of got a life cycle to it as well. This thing's just starting to grow and be born, and so the air is just flowing up and into it. Remember, those sources of lift are what might have gotten this started. Something that kicked it up, got the air moving upward, and now the atmosphere is unstable, so it supports that upward growth of a thunderstorm cloud. At some point, that cloud begins to get tall enough to sustain itself, and at some point it kind of reaches the point of no return. If the cloud gets at least that tall and starts to build up higher than that, then the thunderstorm is very likely. Other times a cloud will billow upward and then it'll just kind of stop. Something fizzles out, maybe it runs out of moisture and the cloud doesn't get significant enough. So once the cloud begins to form, it forms a flat bottom at its LCL, what we call the lifting condensation level. So as air is lifted vertically, it begins to condense at a very precise level. So you see it right along the bottom of the cloud. This is why so many clouds that are this type are very flat on their bottom. When we look at the water vapor condensing, then at some point it gets cold enough in that atmosphere for it to turn not only into liquid but into ice. And you start to see this red line dashed across my picture here. Yours is just a black line on your page, but that line is showing us where the temperature above that line is cold enough to form ice crystals. A thunderstorm definitely has ice in it as well as liquid, and that's why so many thunderstorm clouds can produce little pellets of hail, because there's lots of cold air up there. To some extent, we can look at the cloud and imagine if we could actually see this line. Of course we can't. Meteorologists could estimate where that line would be, but if we could see it in the atmosphere as we looked at a thunderstorm cloud, it's likely to be true that if there's a lot of cloud above that line, that means there's a greater potential for hail to form. If there's not much cloud that's above the ice line in the atmosphere here, essentially, then there's really not a chance that it can form hail. but you'll notice that that line has a lot of cloud above it when we go on to the second stage, and that's why those clouds are likely to have ice in them. Even if it doesn't hail, there's probably ice in there. So this is our second stage, the mature cumulus. Now, no kidding, it's gone a long ways from that first picture to now. That was sort of an immature little baby cumulus cloud. Now we're on to a very mature cumulus cloud. So to go from here to here, I mean, that's a dramatic change. Now there's a lot of things that happened in between. How long did that take? Hours? Half a day? But it's not real long. Typical thunderstorms around here, they start growing in the afternoon and they start to storm by supper time, maybe even sooner, or storm into the night. But they don't last more than just one day. Some thunderstorms will kind of calm down overnight and then kick up the next day somewhere else. But generally there's kind of an ebb and flow in their life, and so a thunderstorm doesn't tend to last terribly long. Not like a mid-latitude cyclone, or certainly not like a hurricane, which can last for over 2 weeks sometimes. So a mature cumulus cloud, this is a big billowing cloud. There's a lot going on here. Some of it's easier to see on the picture that I've got on the screen rather than the one that's on your paper, because the color kind of helps. But notice, you can see here too on your numbers, that this cloud has extended well beyond 40,000 feet, up to even 60,000 feet. Notice it's starting to flatten out. So up on the top of our cloud, and you can see this on your page too, it's beginning to form that flattened top because it's reached the tropopause. Keep in mind, the air in this cloud will only rise as long as it is warmer than its surroundings. And once you reach the tropopause, ozone starts to heat the air up from within. And that's where that UV is converted into heat, and we start to see the cloud unable to rise any further. And when you see a cloud sort of hit that ceiling and spread out vertically instead, make that flat top on top of itself, that's a sign that it's reached maximum height. And now there's a real chance that there's some severe thunderstorm weather to be had from a cloud like that. If you have never paid attention to thunderstorm clouds before, I hope you'll look a little more closely at them this next summer when the first one comes near, so you can kind of appreciate what we're talking about here. It's much cooler when you're looking at a real one that's happening nearby. At this stage of the cloud's growth and the thunderstorm's development, we're seeing both up and down drafts. So strong updrafts, strong downdrafts, and the length of the arrows here, to some extent, will help us to predict the speed of the air going in and out of that thunderstorm. So strong updrafts. We've got some very long arrows here pointing upwards. So that's fast-moving vertical air. We see some even fast-moving air here into the sort of the flat top reaching forward on our thunderstorm. And then certainly in the back of the storm, some very long arrows pointing downward. That's the cold downdrafts that are coming downward with the air. So we have moist air flowing in the front of the storm. And then down the back with the rainfall and perhaps hail, we have cold air blowing down and out. So it's almost kind of a loop here. Air coming up and then air coming down, and it's connected together. In between that, on your diagram, you'll see here a little cold front has been drawn, a little micro-sized cold front, and that's cold air that's pouring out of the storm, wedging under the warm, moist air that's trying to come in. Notice where that cloud's forming. It's in front of that line where the warm air is rising up and chilling as it reaches that temperature where it can start to condense into a cloud. And again, notice how much of the cloud is above the freezing line here. That's a good sign there's a lot of ice up there in that point of the cloud. So 2/3 or even more of this cloud is above the freezing line the way it's been drawn here. Again, as I mentioned before, when you get a flattened anvil top across the top of the cloud, that's a sign that we've hit the tropopause. And there's a lot of folks that if we've looked at the weather balloon data and we know where the tropopause is for that day, a meteorologist can look at a storm cloud and know once it starts to billow out, then it has reached that tropopause, and they can look at the weather balloon data and say, oh, I know that's at 50,000 feet. So that's going to give me a good idea of how tall this cloud is and how much potential it has to be strong. This is the most dangerous stage. It's sort of the mature stage when all the action happens, when the alerts go out, when you hear tornado warnings and watches, when you hear severe thunderstorm warnings and hear about hail and flash flooding. This is where it all kind of happens. So this is the mature stage where the action is, and if you're a storm chaser, this is the one you want to be following and being near. When it hits this most critical sort of peak and climax in its cycle, this is where you want to be there. And getting pictures or putting your instruments inside the storm to try to measure information about it. A mature cumulus cloud at this sort of middle and most important stage again, we can have that cold air blowing out the back of our storm, and that's that downdraft that I mentioned to you before as a possible source of lift. This cold air that you see kind of coming down and out the back of the storm here, that cold air might blow for miles across the prairie here and kick up another storm some miles away. So as that does that, that's how we get a chain reaction. This storm kicks up the next one, that one's downdraft kicks up the next one, and we can have a whole kind of marching line of thunderstorms. And you'll also find that in this area where the air is coming downward in the cold spot here in the back, that's where hail is going to be found. Why is this air so cold? Well, big reason is it's coming from a long ways up, and it's cold up there. Plus, rain is condensed water, and that cold rain that you feel, right, in the middle of a rainstorm, those cold raindrops start hitting you on the back. You've been out in the hot summer heat all day, and now it's starting to rain these cold, icy cold raindrops. Well, that was probably ice just a few thousand feet up, and now it's melted just completely into a water droplet just a few thousand feet above your head. It was still ice. Now it's melted and it's landing on your back. Well, it's going to be cold because it was ice just a little bit ago. It's like someone dripping water out of a cold, icy water bottle onto you. It's going to be cold as well. And that air, that cold air, is dense, so it starts to sink back toward the earth, and that's why it's flowing downward so fast. And the last reason why it's flowing down and is cold is because those cold raindrops cool the air around them, certainly, but they also sort of drag the air with them. So as raindrops by the thousands are falling to earth, they're sort of pulling the air along with them, and that air gets going downward, almost like rain-caused wind here, as we look at the downdraft blowing out the back. This is also the region where it's kind of foggy and gray here to see into it on your picture especially, but on the screen here as well. This is the point in the clouds where tornadoes can often hide. Because there's so much rain that you often can see a tornado go completely invisible and won't even notice that it's there. And you'll hear about this a lot with storm chasers. One of their big frustrations when they want video or to stay safe and not get themselves killed is they don't even know where the thunderstorm is going to produce a tornado necessarily because there's so much rain that it's blacking out their view. So this is where tornadoes are most likely to form as well, kind of right back here in this core area of the thunderstorm. The final stage of the system then is called the dissipating stage. And you can sort of see this top part of this last page you have in your diagrams is sort of the ghostly remnants of this cloud. So those foggy kind of clouds here looks kind of fuzzy on the edges compared to this crisp, billowing, nasty looking cloud. Well, this is sort of the ghostly remnants of that final stage, that's the last stage of the cloud now as the storm dissipates and dissolves, sort of goes away into the atmosphere as the water all evaporates. What happens is eventually something cuts off the updraft. Maybe we just run out of moisture. Maybe the downdraft is so strong, as it mentions here, that it actually pinches off the updraft. What I mean by that is if you think back to the second stage, this cold air flowing down and out can actually flow so far forward that it sort of pinches off the air flowing in. And it's like stepping on a hose. You're pinching off the water flowing through it and nothing more comes out the other end. Well, cold air can do the same thing here and actually sort of pinch off its own inflow, and that makes the storm fall apart. When there isn't warm, moist air coming in, that's the fuel. It's like pinching off the fuel line or the hose, and there's nothing else coming in, so the cloud has to sort of die. The storm has to break down. This tends to happen when the moisture runs out or when nightfall comes and the air cools. You don't have the warm, moist air as much anymore at the surface when the sun goes down and the temperature drops. So the storm potential sort of starts to drop as the sun goes down as well. If it hasn't gotten kicked up and is underway by the time the sun goes down, there's probably a little less of a chance that it would have enough energy to still do that. And at this point in the cloud, you'll notice there are a few arrows pointing upward here, but really all the arrows are pretty weak. But the ones that you see pointing downward, they're a little longer, and those are the most sort of structured ones. There's still some light rain here. I think it probably looks a little bit more clear on my picture than yours, but perhaps you can see it on yours as well. Some light rain here, nothing real heavy. This is sort of those last raindrops where the sun has even started to peek under the cloud now, and it's still sort of finishing out the last rain being squeezed out of those cloud parts that are still available or visible up on the top here. And you might see that the flat anvil top of the cloud is still there as well. So that's the end of our 3 stages of thunderstorm development. So you've taken 2 videos now, one on the ingredients needed for a thunderstorm to start and form, one on the 3 stages of thunderstorm development, and then the third one's going to be on sort of the anatomy of a thunderstorm and some of the areas to look for and some of the features that have names. So if you go on to that third video, switch to the other page that you should have gotten, and we'll fill in some information on there as we go and head toward tornadoes and our sort of capstone of severe weather with those tornadoes that you'll study more in depth.